Okay, so I just want to give a quick disclaimer before we start this video. I'm using a different screen recording program than I normally use, but I've already recorded questions 2 and 4 using the old screen recording. You'll notice that there's a huge difference in volume, audio quality, between this and the previous recording software. So if you go from question to question, you might notice that you have to drastically adjust your volume. So just be prepared for that. Especially if you're going from question 2 to question 3, be prepared for a drastic increase in volume. So you're going to have to drop your computer volume down a lot for that, okay? Just be aware, and yeah, let's get started. It's the 2015 AP Calculus exam. Question 1 reads, the rate at which rainwater flows into a drain pipe is modeled by the function R, where R is in cubic feet per hour, T is in hours. The pipe is partially blocked, so the water is draining out, at a rate modeled by D of T. And initially, there are 30 cubic feet of water at T equals 0. Part A asks, how many cubic feet of rainwater flow into the pipe during the 8-hour time interval from 0 to 8? Okay, so to do this, we need to since we're looking at water flowing into the pipe, we're going to be looking at the function R, because that's telling us the rate at which the rainwater is flowing into the pipe. Okay, so R of T tells us how much rainwater is flowing in at a certain time T, right? You plug in a certain time T into here, you'll get the amount of water that's flowing in at that time. But we want the total amount of rainwater that's flowing over the interval from 0 to 8. So what we got to do is we got to take this function and we got to integrate it from 0 to 8. So we'll integrate R of T from 0 to 8. That's going to get us the total amount of water that's flowing into the pipe from 0 to 8. So if you evaluate this in your calculator, you're going to get 76.570 cubic feet. And the cubic feet, the units, comes from multiplying the units for R of T times the units for T. R of T is measured in cubic feet per hour, and T is measured in hours. So multiplying these two cancels the hours, and you're just left with cubic feet. So there's your answer for part A. This was a 2-point question, 1 point for the integrand and 1 point for the answer. Part B. Is the amount of water in the pipe increasing or decreasing at time T equals 3 hours? Give a reason for your answer. Okay, so we want to look at, is the water increasing or decreasing, right? Easy as that. So when we're looking at the amount of water, we're looking at two factors here. We're looking at the water coming into the pipe and the amount of water coming out of the pipe, right? So if the amount of water coming in is greater than the amount of water coming out, then the amount of water in the pipe is increasing, and vice versa for decreasing, right? So basically, we need to look at the water in minus the water out. Okay, we're just comparing those two. Okay, so the water in, that's given by this function R, right? The water flowing into the drain pipe, and that's R of T. So this is R of T, and the water out, that is given by D of T. That's telling us the rate at which the water is draining out. Okay, so I need to calculate R of T minus D of T. More specifically, since we're at T equals 3 hours, I need to calculate R of 3 minus D of 3, and this will tell me if the amount of water in the pipe is increasing or decreasing at that time. So if I calculate this, I will get negative 0.314. So what does this mean? Well, it means that R of 3 minus D of 3 is less than 0. So it means that D of 3 is greater than R of 3. Okay? So this means that the water that's coming out is greater than the water that's going in. Right? So out is greater than in. So that means the total amount of water is decreasing because there's more going out than there is coming in. Right? So you'd explain this as the amount of water that's going out is greater than the water that's going in because D of 3 is greater than R of 3, so the amount of water is decreasing at time T equals 3. This was a 2-point question, 1 point for comparing R of 3 and D of 3, and 1 point for a correct answer with the correct reason. Okay, that's part B. Part C. Okay, so now we're amping up the difficulty a little bit. At what time T is the amount of water in the pipe minimum? Justify your answer. Okay, so basically first we're going to go and look back at part B, where we talked about this thing R of t minus d of t, and this is telling us the rate at which the amount of water is changing, right? And we use that to determine whether it's increasing or decreasing, right? This is telling us the rate at which the amount of water in the pipe is changing at a certain time t, right? And so we can use this to make some function, let's call it w of t, for the amount of water in the pipe at a certain time, okay? So we know that initially there's 30 cubic feet of water. So we're going to start off with 30, and then we're going to take this guy, and this is going to tell us how much the amount of water is changing. But remember, this is just telling us how much is changing at a certain time. I want to know how much it changed over an entire period of time, so that'll tell me how much it changed from this initial 30. So what I have to do then, just like we integrated r of t in part A, we have to integrate this function in part C. So we have to integrate this entire thing, r of t minus d of t, dt. Okay, and now some people will put a dummy variable here to minimize confusion, because we're all going to integrate this from 0 to t, where t is the specific time that we want. This t is actually different than this t. I'm personally indifferent to it. Sometimes I don't feel like putting in the extra work, but if you would like to be more accurate, you can replace the t's with x's here. Okay, it's because this t and this t are different t's, if that makes any sense. So either way, we have this function, and this function tells us, so you started with 30, and then you changed it by this much, and so that'll tell you the amount of water at a certain time. Okay, so basically what we want to do now is we want to take the minimum of this value. We want to take the minimum of w of t. So we want to minimize this. Okay, that's the ugliest thing I've ever drawn. That's better. Okay, so how do we minimize this? Well, what are you doing there? A differential equation from the 2014 AP video wanted to make a cameo. So, whatever. We're going to move on. We want to minimize this. So what we're going to do is we're going to take the derivative and set it equal to 0, right? So we'll take the derivative to get w prime of t. And so if we take the derivative of this, the derivative of 30 is 0. And then all we have to do is take the derivative of this guy. Okay? And if we evaluate this, remember, by the fundamental theorem of calculus, the derivative and the integral kind of cancel out, so we're just left with r of t minus d of t. That's why the whole t thing is a little bit confusing, because it's not really the same as this. We took this t and substituted it in for here, so even if this was like an x, then we would plug in this t in and we get r of t minus d of t. So if I'm confusing you, just stick with using x's here, and maybe it'll make your life a bit easier. Either way, so we have this guy, and on a new line, we're going to set r of t minus d of t equal to 0, and then if you evaluate this in your calculator to find where r of t is equal to d of t, you get, or you can do r of t minus d of t equals 0. This works too. Either way, you put this in your calculator, and you get t equals 0 and 3.272. Now, we wanted the absolute minimum of this function, so to do absolute extrema, we're going to set up a table. On one end of the table is time, and on the other end is the amount of water at that time. So for a list of times, we're going to put these values along with the endpoints. So in this case, this is one of our endpoints, the other one is 8, and we also have 3.272. So it's all the relative points and the endpoints. Okay? And now what we're going to do is we're going to evaluate w of t at each of these values, right? So for example, if you plug in 0 into w of t, that's going to be 30 plus the integral from 0 to 0 of blah, blah, blah. Remember, the integral from the same number to the same number is just 0. So w of 0 is 30. That makes sense, because initially there's only 30 cubic feet of water. And then, so for the other two things, you take the t values and you plug them into here, and you evaluate this in your calculator. If you do that, for this one you'll get 27.965, and for this one you'll get 48.544, right? So as you can see, there's clearly a minimum amount of water at t equals 3.272. Okay, so you'd say, oh, the maximum is at I'll say at t equals 3.272 hours. Okay, and notice that we gave them the t value because if you look up the initial problem, they didn't ask us for what the maximum amount of or what the minimum amount of water is. They asked us at what time t it occurred. So make sure you don't give them the wrong piece of information there. Okay, so that was our answer. This was a 3-point question. 1 point for taking this r of d minus d of t. 1 point for getting your right answer, and 1 point for the justification. In this case, our table is serving as a wonderful justification. Alright, part D, taking it easy on us here. It was a pretty straightforward part. The pipe can hold 50 cubic feet of water before overflowing. For t greater than 8, water flows into and out of the pipe at the given rates until it begins to overflow. Write, but do not solve an equation involving one or more integrals that gives the time w when the pipe will begin to overflow. Okay, so cool. This is really, really simple because in part C, we actually found the w of t function, which is 30 plus the integral from 0 to t of r of t. No, I'm just going to go with x this time. X minus d of x dx. Okay, so this is the amount of water in the pipe at any certain time. I'm really indecisive. I'll stick with the t. I'm sorry. I want to be consistent from part to part, I guess. So this is our w of t, right? And this is telling us the amount of water in the pipe at any certain time, right? But we want to know, when is the pipe going to overflow? So when is the amount of water in the pipe going to equal 50? So all we got to do is take this guy and set it equal to 50, right? Because we want the amount of water to be 50. So 30 plus the integral from 0 to t of r of t minus d of t is equal to 50, and that's it. Okay, this was a 2-point question. 1 point for the integral here, and 1 point for the entire equation. That concludes question number 1. Let f and g be the functions defined by that and that. Let r and s be the two regions enclosed by the graphs of f and g as shown in the figure above. Part A asks us to find the sums of the areas of regions r and s, but before that, I want to actually think about which of these graphs is f and which of these graphs is g, right? Because they both look like just things, and they don't really label it for us, so some people might be a bit confused, like, okay, which one is which, okay? And we'll have to think about, okay, so you know that x to the 4th graphs, right? Those are the ones that have a maximum of n-1, so 3 turns. So it's going to look something like this, right? If they're the ends are pointing up, it'll look maybe something like that, right? And then if you look here, that closely correlates with this graph, right? If it was going down, it would look something like this, right? But you can see the bumps that's correlating with this graph here, the one that goes like that. And then you see here, 1 plus x plus e to the x squared minus 2x. Well, for this one, if you increase, it just looks like it's going up, 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 up. It's going to look like the exponential kind of thing. And that's more close to this, where it's an exponential graph, right? And I mean, that's the only one left over, so it must be that. So we can label that this is g of x, and this is f of x. Okay, so now that we've got that set, let's actually move on to the question where they want us to find the area of the sums of the regions r and s. Okay, so the first thing they want to do is notice that for these two regions, different graphs are on top and on bottom, okay? So whenever you're dealing with these kind of questions, we want to find the area of a region, you have to identify which graph is on top or which graph's on bottom, right? But in this case, you notice that here, f of x is on the bottom, but here it switches to the top. So we're actually going to have to find the two regions separately and just add them together at the end. We can't just combine them into one integral, okay? So the first thing that we're going to do then is figure out, okay, what's the equation for each of these areas, okay? So for r, I'm going to start by figuring out, okay, so for r, g of x, which is this guy, is what's on top, right? So the top is g of x, and the bottom is f of x, right? Top is g of x, bottom is f of x. And then for s, notice it's the opposite, where the top is f of x, and the bottom is g of x. Right? If you look over to the right and you look at the actual graph, you see, oh, here, on top is f of x, on the bottom is g of x. Okay, so if we want to set the integral, the next thing we have to say is, okay, what is this point here? Because they don't label this point for us. What is the point where this graph and this graph intersect? Because that's going to tell us where R and S meet, where one region becomes the next. Okay, so we need to find the coordinates of this point. And we're going to do that by setting f of x equal to g of x. Okay, so we set f of x equal to g of x, this equal to that. In your calculator, right, you can set 1 is y1, 1 is y2, graph them, find the intersection point. You'll find that the coordinates for that are about 1.033, comma 2.401. Okay, and so I'm not going to store this. I'm actually going to store it as a comma b. In your calculator, you can assign certain variables to certain numbers. So you can assign a to this and b to this. And now whenever I reference a or b in the future, I'll be talking about this point, okay? So now that let me actually go back here, label as a comma b. Okay, so now let's move on. Okay, so we want to find let's start with region of R, okay? And the formula is the integral from a to b, and a and b is not this a to b, it's just a and b, of top minus bottom. A and b are like generic points. Okay, dx. Alright, so for R, we're going to say, okay, R is the integral, and so a and b, we're starting at 0, and we're ending in capital A, right? So we're going from 0 to a, and then top is g of x, minus bottom is f of x, dx. And this is going to give us region R. And to it, we need to add region S. So region S is going to be the integral. And now think about it. Where are we starting and where are we ending for S? Well, we're starting at A, and we're ending at 2. So going from A to 2, in this case, top is f of x, minus bottom is g of x, dx. Right? So again, just to be sure here, this is telling us the region of area of region R. This is telling us the area of region S, and we just integrate these two things. We find the areas of each of those regions, we add them together, and when this is all done in your calculator, because no sane person would do this by hand, you're going to get 2.004 for your answer. Okay, and so this was a 4-point question, right? This was a lengthier one. 2 points for the respective integrands, 1 point for the respective limits, and 1 point for the final answer. Okay, thankfully part B and C are a lot faster than part A. So region S is the base of a solid whose cross-sections perpendicular to the x-axis are squares. Find the volume of that solid. So we're just focusing on region S right now, okay? Basically, we're taking this and we're taking cross-sections perpendicular to the x-axis, right? So we're going this way. And each of these is the base of a square. So you're going to be a square, and you're going to be a square, and you're going to be a square, and you're going to be a square. And we're adding up all these squares to make some sort of a 3D square shape with the base of a weird region S. It's hard to visualize. There's some calculators online that'll easily let you see that. But basically, we're just making a 3D shape, and they want us to find the volume of that 3D shape that we're generating. Okay? So the first thing to do is figure out what is the length of each side of the square. So let me clear this actually for 1 sec. I'm just going to draw one line. Yeah, okay, draw one line. Okay, and so I want to find the length of that in terms of x, right? So just like how we did in part A, to find the length of that, that's basically just going to be top minus bottom. Okay, so top minus bottom. And then remember, so this is region S, right? So I erased the labels, but this is f of x, this is g of x. So in this case, top minus bottom is f of x minus g of x. Okay, so this is the length of the side of the square. So now if I want to find the area of the square, well, that's going to be the side length squared, right? Because this is S. If I call this, I don't know, what's a good letter here that I haven't used yet? W. If I call this W and this W, the area is W squared, right? So we found the length of W, which is the side of the square, and to find the area, we just have to square it. So it's going to be f of x minus g of x squared. Okay, so now what I have to do is I have to integrate this area from this point to this point. So remember, from part A, this is A, and this is 2, and we're going to integrate this area. So we're integrating f of x minus g of x whole squared. Alright, so we're integrating the area of a square, and we're adding up all of these squares from A to 2, and if you do this in your calculator, you're going to get 1.283, and that is your final answer. This was a 3-point question, 2 points for the integrand, 1 point for the answer. Let h be the vertical distance between the graphs of f and g in region S. Find the rate at which h changes with respect to x when x equals 1.8. So I feel like this is the question that's a lot easier than it looks. It looks kind of confusing. You've never seen something like this before, probably, in this context. But it's really not that bad, okay? So, like we've said in part A and part B, the distance between the graphs of f and g, the vertical distance, that's this, right? And like we've said multiple times, that's top minus bottom. That's f of x minus g of x, okay? So this is the vertical distance. This is h, okay? And we want to find the rate at which h changes with respect to x when x equals 1.8. This is code word for h prime of 1.8, right? Because they want the rate of change of x when, they want the rate of change of h when x equals 1.8. So they're just asking us for h prime of 1.8, and we have h, so we can easily find h prime of 1.8. So we'll start by taking the derivative, h prime of x. That's simply going to be f prime of x minus g prime of x, and h prime of 1.8, therefore, is f prime of 1.8 minus g prime of 1.8. And if you evaluate this in your calculator, you get negative 3.812. This really feels more like a calculator exercise than a calculus exercise, to be honest with you. There's a lot of plugging in equations and numbers in your calculator, but it is what it is, right? So, that's it. That's the rate at which h changes when x is equal to 1.8. But that's the key word here. And then this was a 2-point question, 1 point for finding h prime of x, and 1 point for the final answer. Question 2. Question 3. Joanna jogs along a straight path. For t between 0 and 40, her velocity is given by the differentiable function v. Selected values of v of t, where t is measured in minutes, and v of t is measured in meters per minute, are given in this table. In part A, we're asked to use the data in the table to estimate the value of v prime of 16. Alright, so whenever you see this thing where they ask you to approximate the derivative given the values of that function in a table, you're always going to be taking 2 points that are close by. So in this case, we have v prime of 16, so our 2 close by points are going to be 12 and 20. And we're going to be taking the slope between these 2 points. Because basically, we're using 2 points that are nearby as an approximation for the slope at 1 point that's in between those 2 points. Okay, so in this case, what we're going to do is we are going to find the slope between 12, 200 and 20, 240, right? So v prime of 16 is approximately equal to v of 20 minus v of 12, y2 minus y1 over x2 minus x1, 20 minus 12. And you can see here this is 240 minus 200. That's not 240. Minus 200 over 20 minus 12 is 8. So this is going to be 40 over 8, which is 5. Okay. Now in terms of the units for this, we need to think about, okay, so we have here velocity on the top and time on the bottom, right? So velocity is in meters per minute, so it's going to be meters per minute. And the denominator, we have minutes, divided by minutes. And this is going to be equal to meters per minute squared. So we have meters per minute per minute. So the units for the derivative of the velocity is going to be meters per square minute. Okay? This was a 1-point question, 1 point for the correct answer. Using correct units, explain the meaning of the definite integral, the integral from 0 to 40 of the absolute value of the velocity in the context of this problem. Okay, we're going to approximate that using a right Riemann sum with the 4 subintervals indicated in the table. Okay, so what we're going to do is we're going to start off with what is the integral of velocity? Sorry, not the integral of velocity, the absolute value of velocity. Well, the absolute value of velocity is speed. Right? If you've ever seen the thing, I am you've seen this from cars, right? That's where the absolute value of velocity is speed, right? So the integral of the absolute value of velocity, therefore, is the integral of the speed, and the integral of the speed is distance. Okay? So if we're integrating the speed from 0 to 40, that's going to give us the total distance traveled between 0 and 40, right? I'll go to the equal sign. It is the total distance traveled by Joanna. Okay. Over t between 0 and 40, over t between and it's in meters. Okay, so that is your explanation. Now we need to approximate the value of it using a right Riemann sum with 4 subintervals, right? So the 4 subintervals that we're talking about are 0 to 12, 12 to 20, 20 to 24, 24 to 40. 4 subintervals, okay? And what the right Riemann sum is going to be is going to be the difference between the t values times the right of the 2 velocity values. Okay, so in this case, it's going to be the difference between 0 and 12 times the one on the right, which is 200. Okay? Oh, and by the way, it's important. Since we're dealing with absolute value here, we're going to be taking the difference in time multiplied by the absolute value of the velocity on the right. Okay? So the Riemann sum is going to be, why am I on black? The integral from 0 to 40 of absolute value of the velocity is approximately equal to, so we have, like I said, the difference between 0 and 12, which is 12, times the absolute value of this right point, which is 200. So we're going to have 12 times the absolute value of 200 plus the difference between 12 and 20, which is 8, times the absolute value of this right one, which is 240, plus 8 times the absolute value of 240, plus the difference between 20 and 24, which is 4, times the absolute value of this right point, which is 220. So it's going to be 4 times the absolute value of negative 220, plus the difference between 24 and 40, which is 16, times the right, which is 150. So plus 16 times 150, and once you can calculate that, you will get 7,600 meters. Okay, so this was a 3-point question. 1 point for the explanation of what it means, 1 point for the Riemann sum, and 1 point for the correct answer. Okay, part C. Bob is riding his bicycle along the same path. For t between 0 and 10, Bob's velocity is modeled by blah blah blah, where t is measured in minutes and b is in meters per minute. Find Bob's acceleration at t equals 5. Okay, this is an incredibly straightforward, simple problem. So we're lucky that they gave this to us. To find this equation, all we have to do is think about, okay, how can I relate the velocity to the acceleration, right? So I have b of t. How do I relate that to b prime of t? Or I can't give you the answer there. How do I relate this to the acceleration? And well, the answer is that if you take the derivative of the velocity, you get the acceleration. Okay, so to find the acceleration at time t equals 5, we want the derivative at 5. Okay, so first let's start off by finding b prime of t, and that's going to be a simple application of the power rule to get us 3t squared minus 12t. So to find b prime of 5, we'll simply plug in 5 into here, and I'll get 3 times 25 minus 12 times 5, which is 75 minus 60 is 15. And then the units are going to be the units for velocity over the units for time. Like we did last time, it's going to be meters per square minute. Okay, that is b prime of 5. This was a 2-point question. 1 point for dealing with b prime of t, and 1 point for the correct value of b prime of 5. Based on the model B from part C, find Bob's average velocity across the interval 0 to 10. Okay, so this is another simple application of the average value formula. Right, so let me just recap. The average value formula is if we want the average value of f of x over AB, well, that's going to be 1 over b minus a times the integral from a to b of f of x dx. Okay, so now if we want to find the average value of b across the interval from 0 to 10, we can just plug those numbers into here, and we're going to get 1 over a is 0 and b is 10, so b minus a is going to be 10 times the integral from 0 to 10. Instead of f of x, we'll put b of t. Okay, and since this is in the no calculator section, we're evaluating this integral old school by hand. And we're going to get t cubed minus 6t squared plus 300. Thankfully, it's not the hardest integral in the world to evaluate. It's just going to be raising this up and dividing. So we'll have the 1/10 still hanging out here for fun, times t to the 4th over 4. Remember, we add 1 and we get 4 and we divide. And then minus, we add 1 to get 3, we divide. So we'll get 2t cubed, 6 over 3 is 2, plus 300t. And we're not including a plus c because this is a definite integral. We have bounds that are 0 and 10. Notice if I plug in 0, it's just going to wipe everything out. I'm just going to get a whole bunch of zeros. So I'm just going to plug in 10. Okay, I'll get 10 to the 4th over 4 minus 2 times 10 cubed plus 300 times 10. And yeah, that's it. There's the average value of the velocity. And the units for this are going to be the same as the units for velocity because this is the average velocity. And the units, remember, are meters per minute. So that is the units there as well. Obviously, I didn't take the time to evaluate all this. You could easily do that, but I feel like I'd mess up a 0 somewhere. That's totally something I'd do. So better to be safe than sorry and just leave it like that. Okay, this was a 3-point question. 1 point for 1 point for the integral, 1 point for the antiderivative of that, and 1 point for the final answer. Alright, so that concludes question number 3. Let's move on to the next one. Question number 4. Consider the differential equation dy dx equals 2x minus y. On the axes provided, sketch a slope field for the given differential equation at the 6 points indicated. Okay, so this is basically just taking different combinations of the points, plugging them into here, and figuring out what dy dx is. And dy dx is going to correspond to the slope at that point. So for example, at 1, 1, if we plug in 1 into x and y, the dy dx is 1. So that means I'm going to draw a slope of 1 here. Okay, something like that. And then here at 1, 2, this value, dy dx is going to be 0, right? 2 minus 2. So I'm going to draw a flat line there for a slope of 0. And then at 1, negative 1, my slope is going to be 3. So I'll have a very steep slope. And then, just like that, here the slope is 0, -1, so the slope is 1 again. At 0, 1, the slope is -1. And at 0, 2, the slope is -2. Okay? And there we go. Not perfect, but it's a slope field. Okay? This was a 2-point question. 1 point for all the values. What's happening? 1 point for all the values where the slope is 0, and another point for all the values where the slope is 1. Okay, as you've noticed, I've gotten rid of the slope field because that was a bit too much in terms of space. So let's keep going. Part B. Find the second derivative in terms of x and y. Determine the concavity of all solution curves for the given differential equation in quadrant 2. Give a reason for your answer. Okay, so this is a relatively simple differential equation, so it shouldn't be too hard to take the second derivative, right? So take the derivative, and then we'll say, okay, so with respect to x, this is just going to be 2, and with respect to x, this is going to be 1 times dy dx. Basically, remember, whenever you're dealing with y's, you just take the derivative like normal, and then you stick a dy dx on the end. Okay? So this gives 2 minus dy dx. But they wanted it in terms of x and y, so what you do here is you know that dy dx is equal to 2x minus y, so I can substitute that in here. So I'll get 2 minus 2x minus y, which is 2 minus 2x plus y. Okay? And that is the second derivative. And then now they wanted the concavity of all solution curves for the given differential equation in quadrant 2. Okay, so remember, if we have our xy plane here, we have quadrant 1, 2, 3, and 4. And so quadrant 2 is where the x values are negative and the y values are positive, right? So we have a negative x value and a positive y value. So since we're subtracting the x values, if we're subtracting a negative number, this is going to be a positive thing. It's negative 2x. And then y is a positive, so we're adding a positive number. So this is 2 is positive, and then we're adding, and then we're adding again, right? So positive, positive, positive. So that means in the second quadrant, the second derivative is going to be positive, right? And since the second derivative is positive, remember, second derivative is positive, that means it's concave up. That means f of x is concave up, okay? So what you'd say is that the second derivative is greater than 0, since x is less than 0 and y is greater than 0, so the solution is concave up in quadrant 2. This was a 2-point question, 1 point for correctly coming up with the second derivative, and 1 point for stating that the solutions are concave up with the proper reason to accompany it. Let y equals f of x be a particular solution to the differential equation with the initial condition f of 2 equals 3. Does f have relative minimum, maximum, or neither at x equals 2? Justify your answer. Okay, so basically remember, what happens when we have a relative extrema, so a relative minimum or relative maximum, I'll draw a relative minimum here, is that the derivative switches signs. So it goes, for example, here it's going from negative to 0 to positive. If it was a relative maximum, it would go from positive to 0 to negative. Either way, note that it's crossing through 0, okay? So when we try to figure out, okay, do we have a relative minimum, maximum, rather, so do we have a relative extrema? If we take the derivative to find the slope at this point, this is 2, 3. I don't know if it's going to be a minimum or maximum. I'm just drawing a generic thing here. So if we take this and we evaluate it at 2, 3, to figure out the slope at this point, it should be 0. We find that if we plug in 2, 3, we'll get 4 minus 3, which is 1, which is not equal to 0, right? So that means we can't have a relative minimum or a relative maximum because the slope at that point is not 0, okay? So you'd say that the derivative is not equal to 0 at the point 2, 3, so there is not a relative minimum or a relative maximum at x equals 2. This was a 2-point question, 1 point for considering the derivative at the point 2, 3, and another point for the correct conclusion with the justification. Okay, part D. Find the values of the constants m and b for which y equals mx plus b is the solution to the differential equation. Okay, to be honest with you, this question stumped me at first. I had absolutely no clue what to do here, and it took a long time to understand what was going on, but now I think I got it and I can explain it to you. But I can guarantee you, if this was on the exam, there was no way I would have gotten it, especially in the time pressure. Okay, so let's start off by looking at this. We have y equals mx plus b is a solution to this differential equation, right? So what I can do is, since I know this equation, I can take the derivative of it, and I'll have that, right? So if I take the derivative of this, I'll get dy dx equals, and if I take the derivative on this side, this becomes m, and b is a constant, so that just drops off, right? So I get that the derivative is equal to this constant m. And I know that it's equal to 2x plus y, so I can say, alright, well, this is equal to 2x minus y, right? Since I know that the derivative is equal to 2x minus y, and it's equal to m, that means m is equal to 2x minus y, right? Okay, and now I can say, alright, I know y is equal to mx plus b, so I can take mx plus b and plug it in here for y. So I'll get m is equal to 2x minus mx plus b, and if I simplify this, I'll get m equals 2x minus mx minus b, so m equals 2 minus m x minus b. Okay, now what I can do is I can take the derivative of both sides, because if I do that, something really good is going to happen. Okay, remember, m is a constant, right? Constants m and b. So if I take the derivative of m, it's just going to become 0. And then on this side, I can take the derivative of 2 minus m times x. Well, this is like the coefficient, so I'm just going to get 2 minus m, and the minus b drops off. And suddenly we have a nice equation here where we can just solve for m, and we get m equals 2. Okay, so all we have to do now is figure out b, right? And thankfully, finding out b is a lot more easy than figuring out m, right? Because we know that the solution is going to be in the form y equals mx plus b, right? So I can take 2 and plug it back here for m, so I'll get 2 equals 2x minus y. If I solve it to get it in the form y equals mx plus b, I'll add the y and I'll subtract the 2, and I'll get y equals 2x minus 2. And you can clearly see in this situation, m equals 2 and b equals negative 2. Okay, and those are the answers for m and b. This was a 3-point question. 1 point for taking the derivative of mx plus b and getting m. Another point for setting that equal to 2x minus y. And then a third point for getting m equals 2 and b equals negative 2 as your answers. Okay? And with that, we're done with question 4. Oh, actually, before that, I want to actually add one tidbit. If this question was difficult for you as it was for me, just skip it. Don't worry about it. It was only 3 points, as you can see, right? So I just go back and come to this and do some random stuff to get a few pity points if you can. But don't waste your time trying to figure this out and be like, why isn't this working, when there's so much other stuff you could do that's so much easier that is the same amount of points. Okay, so just a test-taking strategy there. Don't waste your time on any particularly difficult part. Okay, question number 5. The figure above shows the graph of f prime, the derivative of a twice differentiable function f, from negative 3 to 4. The graph of f prime has horizontal tangents in negative 1, 1, and 3, and the areas bounded by x-axis and f prime on negative 2, 1, and 1, 4 on 9 and 12 respectively. Okay, so let's label these things that it's talking about here. So it says the graph of f has horizontal tangents at negative 1, 1, and 3, right? So at negative 1, 1, and 3, it has a horizontal tangent, which means it's a flat tangent line. Okay? And we also know that the areas bounded by the x-axis and the graphs of f prime from negative 2 to 1, so that's this region, and 1 to 4, that's this region, are 9 and 12 respectively. Okay? But notice that they're actually below the x-axis, so the areas would be considered negative. So from negative 2 to 1, it's actually negative 9, and from 1 to 4, it's actually negative 12. Now part A asks us to find all the x-coordinates where f has a relative maximum, and to give a reason for our answer. Okay, so remember, we're not looking at f prime, we're looking at f. So if f has a relative maximum, it would look something like this, right at the top of a hill. And if we look at the top of this hill, we notice that up on this part, it has a positive derivative, right? Because the slope is up, like that. But on the other side, it has a negative derivative. Slope is down. So at this maximum point, the derivative switches from positive to negative. Switches from positive to negative, okay? Now what we have to do is we have to go to our graph and look at where it switches from positive to negative. And we see that there's only one point where that happens, and that's at -2, right? You can see it starts above, it's positive, and then at -2, the derivative switches to negative. So here's the point where f prime switches from positive to negative. That's right here. So you'd say that, well, okay, f prime switches from positive to negative at x equals -2, so f has a relative maximum at x equals -2. Okay, this was a 2-point question, 1 point for the answer, 1 point for the explanation. Part B. On what open intervals contained in -3 to 4 is the graph of f both concave down and decreasing? Give a reason for your answer. Alright, so this is difficult because at first glance it seems like, okay, f is concave down and decreasing, what does it have to do with f prime? So what we're going to do is we're going to take these facts about f and ask ourselves, okay, if f is concave down, what does it tell me about f prime? And if f is decreasing, what does that tell me about f prime? Because all my information is about f prime, right? So I'll figure out what this is asking me about f prime, and then we'll look at f prime and determine our answer. Okay? So we'll start off with f is concave down. So f is concave down. So what do I know about that? Well, when I think of concavity, when I think of concave down, I think that the second derivative is negative. Okay? The second derivative is negative, so it's concave down. And well, if the second derivative is negative, that must mean that the first derivative is decreasing. Okay? The first derivative is decreasing, the second derivative is negative, right? The slope of f prime is negative. Okay? So if f is concave down, f prime is decreasing. And now we can do the same thing for the other piece of information we're given. F is decreasing. Okay? Well, I can tell you right away that if f is decreasing, then f prime is negative. Okay? So basically, when they're asking where is f both concave down and decreasing, they're really asking where is f prime decreasing and negative. So it's got to be going down, or it's decreasing, and it's got to be under the x-axis. It's got to be negative. So if we go ahead and shade all the regions on the graph that correspond to that, we'll see that here it's going down, but it's positive. And then here, it's going down, but it's negative. So here, this part meets our criteria. Here it starts to go up. It's negative, but it goes up. And then here, it goes down and it's negative again. So this part, again, meets our criteria. And then here it stops, and then it switches to going up. So it's increasing there. Right? So we found two distinct sections on our graph that meets our criteria. So you'd say f is concave down and decreasing from -2 to -1, and from 1 to 3, because f prime is decreasing and negative on those intervals. This was a 2-point question, 1 point for the answer, 1 point for the explanation. Part C. Find the x-coordinates of all points of inflection for the graph of f. Give a reason for your answer. Okay, so this is really straightforward, right? Points of inflection means that the derivative switches, the second derivative switches sign, right? So whenever f has a point of inflection, what that means is that the second derivative switches sign. So the second derivative might switch from positive to negative or negative to positive. Okay, so like from here, for example, approximately here is a point of inflection on f prime, not f, on f prime, because you can see it switches from concave up to concave down. So the second derivative switches sign at x equals 0 here. But ignore that because we're looking for the inflection points of f, not the inflection points of f prime. Okay, so we want to figure out where does f double prime switch sign, and well, okay, if f double prime switches sign, what does that tell me about f prime? Well, if f double prime switches sign, well, that means that f prime switches direction. Okay? So I want to figure out where on my graph does f prime switch direction, right? And so I can clearly see, looking at this graph, that where does it switch direction? Okay, so we're going down here and we go up. So here's the switch in direction. And we can see it goes up and then it goes down. So here's the switch in direction. And then it goes down and then it goes up. So here's the switch in direction. And that's really it. We found the 3 points. -1, x equals -1, x equals 1, and x equals 3. On all these 3 points, f has an inflection point because f prime switches direction. So that would be our explanation. And this was a 2-point question. 1 point for the answer and 1 point for the explanation. Part D. Given that f of 1 equals 3, write an expression for f of x involving an integral, and find f of 4 and f of -2. Okay, so we know that f of 1 is 3, and we want to find an expression for f of x with an integral. Okay, so basically, first of all, we're given this value f of 1, right? And what we're going to do is we're going to say, okay, I want to find f of x, and I know f of 1, right? So the two kind of x values that I'm interested in dealing with are 1 and x, right? So what I do is if I can integrate the derivative of these two functions, which is f prime of x, and integrate it from one of these points to the other point, so from 1 to x, I will get the answer that I want. Okay? So if I integrate this, I'm going to get f of x minus f of 1. By the fundamental theorem of calculus, the integral and the derivative cancel out, and I'll just get f of x minus f of 1. Okay? So, now since I know f of 1, and I want f of x, I can solve this for f of x. F of x equals f of 1. Remember, f of 1 is just 3. So we'll say 3 plus the integral from 1 to x of f prime of x dx. Okay? So this is the expression for f of x that involves an integral. Now, we want to use this to find f of 4 and f of -2. So f of 4, we'll plug in 4 in for x, and we'll get 3 plus the integral from 1 to 4 of f prime of x dx. What is this integral from 1 to 4 of f prime of x dx? Well, remember, integral is the area under a curve. So if we go here, the area under a curve from 1 to 4, we said that's -12. So we can say that f of 4 is 3 plus -12, which is 3 minus 12, which is -9. Okay, and that's the value of f of 4. Now, for f of -2, on the other hand, you'll notice something interesting happens when you try to integrate. You'll go from 1 to -2, and that's kind of weird because we're going from the bigger number to the smaller number, right? So the way we avoid dealing with that confusion is we can simply switch the bounds of the integral, switch the order of the bounds, if you change the sign in front. So I can switch the plus to a minus, and I can switch the order of the bounds, -2 to 1. Because you always want to go from the smaller number to the bigger number. Okay? So what is this? Well, the integral from -2 to 1 of f prime of x dx is the area between -2 and 1. And if we go here, the area from -2 and 1 is -9. So I can go down here, and I can say that this is equal to 3 minus -9, which is 3 plus 9, which is 12. Okay, so that is f of -2. This was a 3-point question, my bad. 3-point question. 1 point for the f prime of x part, the integrand, 1 part for the expression for f of x, and 1 point for finding f of 4 and f of -2 combined. Okay, that's question number 5 done. Question number 6. Consider the curve given by the equation y cubed equals xy minus 2. It can be shown that dy dx equals y over 3y squared minus x. Part A asks us to write an equation for the line tangent to the curve at the point 1, 1. Okay, So whenever you see they ask you to write the equation for the tangent line, you always need to write down two things: point and slope. Okay? So you want to write down the point and the slope. Luckily, they've been very nice. They gave us the point. It's -1, 1. For the slope, remember the slope is the derivative at a particular point, right? So we want to take the derivative at the point that we're interested in. In this case, it's -1, 1. So to do that, we'll take -1 and plug it in whenever we see x. We'll take 1 and plug it in whenever we see y. So if we do that, we'll plug in 1 over here over 3 times, plugging in 1 again for y, so 1 squared minus x, so minus -1. That's going to be 1 over, remember 1 squared is 1, so 1 times 3 is 3, so just 3 minus -1. The two negatives are going to cancel, and we'll get 3 plus 1, which is 1 over 4. Okay, so we found the point, and we found the slope. Now we can put these together to find our tangent line, okay? So we should plug it into the formula. So we have y minus y1, and y1 is 1. So y minus 1 equals m, which is our slope, so 1/4, times x minus x1. So x1 is this -1, so we'll get x minus -1, so it's going to be x plus 1. And this is our tangent line. Okay, this was a 2-point question. 1 point for successfully finding the derivative at the point -1, 1, and the second point for the correct tangent line equation. Part B. Find the coordinates of all points on the curve at which the tangent line to the curve at that point is vertical. Okay, so whenever we're dealing with a vertical tangent line, what that means is that the derivative does not exist. So in this case, well, that's going to happen when our denominator is equal to 0, right? If our denominator is equal to 0, we'd be dividing by a 0, so our derivative would not exist. What we're going to do is we're going to take 3y squared minus x and set that equal to 0. This is going to give us all the points where the tangent line is vertical, okay? What I can do now is I can solve this for x, and I'll get x equals 3y squared, right? And you might be thinking, hang on, there's only one equation. How do I figure out a coordinate from this one equation? There's an infinite number of points. Well, that's where the other curve comes in. Or not the other curve, but like the other equation. We're going to take this x equals 3y squared and substitute it into here. So we'll get y cubed minus, and I'll take in 3y squared and plug it in for x. So I'll get 3y squared here times y equals 2. Okay? If I simplify this, I'll get y cubed minus 3y cubed. Because remember, you multiply, you're going to add the exponents. 2 plus 1 is 3. Equals 2. I can simplify this. 1 minus 3 is -2. So -2y cubed equals 2. I can divide by -2. So y cubed equals -1. And I can take the cube root of both sides. And I'll get y equals -1. Okay? So now how do I figure out the x component of this? Well, I can take this and plug it back into this expression we had earlier, right? So x equals 3 times -1 squared. And well, -1 squared is just 1, so this is just equal to 3. So the point is 3 comma -1, right? X comma y. It's going to be 3 comma -1. And that is it. This was a 3-point question. 1 point for setting the denominator equal to 0. 1 point for substituting the result you got into the other equation, the equation for the curve. And then the 3rd point for the correct point, 3, -1. Part C. Evaluate the second derivative at the point on the curve where x equals -1 and y equals 1. Okay, so we were given the first derivative, and now we have to take the second derivative, okay? So, the second derivative, get ready for some equations here, because this is going to get a little bit mathy, which you should expect being in a math class, but whatever. We want to take the second derivative, and to take the derivative of this, we're going to use the quotient rule because we're dividing. So the quotient rule is going to be the bottom one times the derivative of the top one. The derivative of y with respect to x is dy dx. Okay, minus the top one times the derivative of the bottom one. The derivative of this is going to be 6y dy dx. Because remember, when you multiply, whenever you take the derivative of something with respect to y, and you're doing with respect to x, and you're doing implicit differentiation. So you're differentiating y with respect to x. You do it like normal, but you added dy dx on the end. So that's why we did the 6y like normal, then we added dy dx on the end. And we're subtracting 1, because the derivative of x is 1. And this whole thing is being divided by this bottom thing squared. So 3y squared minus x whole squared. Okay? Now, we're not quite done yet, because we can't simply have a dy dx here. I mean, you could, but the way we're going to solve this and get everything in terms of x and y, because we can't simply plug in, x and negative 1 comma 1 into here, right? So what we're going to do is we're going to replace this dy dx with something in terms of x and y. And they very, very nicely have something here with the derivative in terms of x and y. So I'm going to take this dy dx and replace it with y over 3y squared minus x. And then my second derivative will be completely in terms of x and y's, so we'll just be able to plug in x equals negative 1 and y equals 1 into those x's and y's. Okay, so it's going to be equal to 3y squared minus x times dy dx, so times y over 3y squared minus x. I'll be subtracting y times 6y times y over 3y squared minus x. Remember, this is the y, this is 6y, and the dy dx minus 1, and then the other thing still stays. Okay, now notice that I could plug in right now, but I'm really noticing that these guys can just cancel out. That might make my substitutions a little bit easier, right? And I can also go ahead if I want to and distribute in this region. So this part is just going to be y, right? So y minus, if I distribute this, I'll get a y times a 6y times a y. That's going to be minus 6y cubed over 3y squared minus x. And if I take this y and distribute it to the 1, it's negative y times negative 1, so that's going to be a plus y. And then this guy still stays. And then y plus y is 2y, so I'll get 2y minus all of this stuff that was there before. Right? So now we've simplified this pretty good. I don't see any need to go any further. Now all we have to do is plug in the x and y values that we were given into the second derivative. Okay, so we were given the point negative 1 comma 1. So the second derivative at negative 1 comma 1. I'll just plug in negative 1 for x and y for 1 into everything here. So 2 times 1 is 2 minus 1 cubed is 3, so 6 times 1 cubed is 6 over, and then 3 times 1 squared is 3, 3 minus a negative 1, that's going to be 3 plus 1, that's going to be 4, and I'm dividing by, well, we just said that this thing is 4, so it's going to be 4 squared is 16, alright, and I'm honestly just going to leave it like that and call it a day. You could simplify this further. If you simplify this further, you'd get 1 over 32, but this is totally sufficient because it's numerically equivalent to the correct simplified answer. Okay, so this was a 4-point question. You got 2 points for successfully taking the derivative, just the implicit differentiation part. You got another point for substituting stuff in for dy dx, and you got a final point for the correct numerical answer. That's question 6, and we are done with this AP exam video. I hope you liked it. Please like and subscribe and whatever else I'm forgetting, because I don't know how to do YouTube. And I'll see you in the next video. Goodbye.